When you're doing data analysis, having the right tool for the job, well, it's pretty much everything. Sometimes you need this huge master blueprint that shows how every single part of a system works together. But other times, you just need a specialized wrench for one specific task. Today, we're stocking our statistical toolkit with two absolutely essential concepts: joint and marginal probability. Let's get into it and see how they fit.
So, here's the game plan. We'll kick things off with the big picture, what I'm calling the master blueprint. Then we'll see how to forge a simpler, more focused tool right from it. After that, we'll put these tools to the test on a few jobs, see how they can team up to answer some tricky questions, and finally, we'll wrap it all up so you always know exactly which tool to grab. Okay, part one, the master blueprint. This thing is all about tackling a really fundamental challenge you're going to face in pretty much any kind of data analysis.
Think about it. Things in the real world, they're rarely isolated, right? The temperature and the humidity, how much you spend on ads and what your sales look like, inflation and unemployment, these things are connected. So the big question is, how do we create one single mathematical description that captures that entire relationship?
Well, the answer is the joint probability density function, and I really want you to think of it exactly like a master blueprint for a complex machine. It holds every single piece of information about how two variables, let's just call them x and y, behave together. It is the one single source of truth for the entire system.
And for this whole explainer, we're going to stick with this one specific blueprint. This function, f of x comma y, describes the complete relationship between our two variables, x and y, within these specific ranges. Every single question we could possibly ask about this system, the answer starts right here.
Here's the catch with master blueprints. They are incredibly detailed, which is amazing, but sometimes it's just overkill. Sometimes you gotta zoom in.
Like, what if your boss doesn't care about the whole complex system? What if they just come up to you and ask, hey, forget about y for a minute. Just tell me about x. What's the chance x is going to be over a certain value? Well, that master blueprint doesn't immediately tell you that. For that, we need to forge a new tool. And that tool is the marginal probability density function. So if the joint PDF is our master blueprint, the marginal PDF is like the custom wrench we craft from it. It's built to do one job and one job only. Tell us everything about a single variable, completely isolated from the others. So how do we make one? We start with our joint blueprint, and then we use a process from calculus called integration. Now, don't worry about the term, just think of it as collapsing the blueprint. To get the story of just x, we basically sum up all the probabilities across the entire range of y. We're effectively averaging out its influence, getting it out of the picture, and that leaves us with a crystal clear function for x all on its own. And when we do that process on our main example, we get these two awesome specialized tools. Over on the left, we've got the marginal function just for x. All the info about y has been stripped away. And on the right, we've got the marginal function just for y. So now our toolkit is complete. One master blueprint and two specialized instruments. All right, our toolkit is assembled. Time to put it to work. We're going to tackle a few probability jobs. And for every single one, the first and most critical step is picking the right function. Okay, first task up. A pretty straightforward question. What are the chances that our variable x takes on a value greater than 1? So how do we pick our tool? Well, you just have to look at what the question's asking. It is only about x. It doesn't mention y at all. And that's our cue. That tells us to grab the specialized tool, the marginal function for x. We do not need the complexity of the master blueprint for this job. So we use that marginal function, run the numbers, and bam, we get our answer. 19 over 24. That's about 79%. See, our specialized tool made that job nice and simple. All right, next job. Same idea, different variable. What is the probability that y is less than 1/2? And again, we just pause and think. The question is exclusively about y, no mention of x anywhere. So we reach for our other specialized tool, the marginal function for y. It's the perfect instrument for this. A little bit of math later, and there's our answer, 1/4 or 25%. Simple, clean, efficient, all because we used the right tool for the job. Okay, time to throw a little curveball. Job number 3. What is the probability that x is greater than 1 and y is less than 1/2? Did you see that word? And. That's the signal. That one little word tells you this is no longer a job for a specialized wrench. We're being asked about x and y at the same time. We need to know how they behave together. So, we have to go back to the beginning.
and pull out our master blueprint, the original joint function. And by using that master blueprint, the one that understands the entire relationship between both variables, we find out the probability is 5 out of 24.
So up to now, we've been using our tools separately, but the real magic happens when we start combining them to answer even more interesting conditional questions.
And here it is, the final and trickiest job. What is the probability that y is less than 1/2, given we already know that x is greater than 1? This is what's known as a conditional probability. And this is where our whole toolkit just comes together so beautifully. The formula here says the probability of A happening given B already happened is just the probability of both happening divided by the probability of just B happening. For us, A is y less than 1/2 and B is x greater than 1. And if you look closely, we've already done all the heavy lifting. The probability of A and B was our joint probability from job 3, and the probability of just B was our marginal probability from job 1.
We literally just plug in the answers we already found. The 24s on the bottom cancel out, and we are left with our final answer, 5/19. Because we built our toolkit the right way, this really complex question just turned into simple arithmetic.
Okay, let's zoom out one last time and put our two main tools side by side, just to make this distinction absolutely crystal clear.
So here's the key takeaway, the thing to really lock in. The joint function, that's your master blueprint. You grab it when your question involves x and y. It's for understanding the whole system. The marginal function, that's your specialized tool. You make it from the blueprint, and you use it when your question is about x alone or y alone. It's for zooming in on just one piece of the puzzle.
And look, this isn't just some abstract math exercise. An economist models the joint behavior of inflation and unemployment, but then they need the marginal view to focus just on an unemployment forecast. A meteorologist models temperature and humidity together, but you might only care about the marginal probability of the temperature dropping below freezing. In business, you model how ad spend and sales move together, but the marketing team needs that marginal function to figure out their budget. It's such a powerful way of thinking, to see the whole system, but also have the power to zoom in on any individual part. It's the difference between seeing the whole forest and being able to study a single tree. So now that you have these tools, think about it. What complex system out there in your world would you want to model and understand?